Hello guys, welcome back to my YouTube channel. Today we'll be dealing with strength of material. This is N5, right? This is an introduction, right, to strength of material, which is module 1. So here we simply want to remind you about force, what force causes. If you remember what force causes, it causes to tends, it causes or tends to cause a change in motion or the shape to body. To define the force completely, we must indicate the following: point of application, where force is acting on the body, magnitude, direction, its nature, indicate whether it's pulling or pushing. Mostly will here in strength of material will be dealing with changing the deformation, changing of the shape, how force shape, how force influence the shape of an object. As you can see here, we have types of forces. Types of forces will be, as you can see here, they say there are 5 types of forces that can work in any component or structure, namely tensile. As you can see there, we have the stresses, the name of type of forces, namely tensile, compressive, shear, bending, torsional force. These occur on their own or in combination, right? So number 1, we have a tensile force. What is the tensile force? Tensile force, what does tensile force actually causes? Tensile force stretches material by pulling on the object or the member of the structure as shown in figure 1.3. Let's check 1.3 here. You see when we are pulling, this is a tensile. At the middle part, you see the dimension will change and become small. It's like we're pulling, it's a pulling force. And then we focus mostly, you see the cross section where we apply the force on that cross section. Most when you're doing calculation, we'll be focusing on that. As you can see, then number 2, we have a compressive force. A compressive force on pushes on an object and tends to flatten it or to make it short. As you can see, you compress, you see the area indication, it makes it smaller. You see here in the middle becomes big. You squeeze it, you make it smaller. We call it compression, which when you make the object become small by applying forces. You see those cross section and applying down the cross section. So that's it's a compressive. Then number 3, we have a shear force. A shear force makes one part of an object slide. You're right. Object slide part another part as shown in figure 1.3. Too much shearing force will cause material to suddenly fracture. An example, in cutting wire with a pair of pliers, as you can see here, will cause this to tear up then or to fracture. Will tear up or will fracture. The shape will be something like this shape, like something like that. Will change the direction, would be like this. When you apply that, this object will sort of change like that. So this is a shear. So when you applied forces in the opposite direction of an object at a certain point, talking about shear. Then bending force, this one we know it. It's a bending couple or bending object. This we know it. This is the one that we apply it from the beams. With this one we know it. When we apply the forces here, you see there will be a bending there. There will be a bending. Then this one, it's a twisting. You try to twist, but nevertheless, what you must know, I show you what we'll calculate here. Okay, you will see this. We have 5. This they goes in hand. Torsion here, it has its own topic alone. This is not will be, there's its topic alone. This when we are talking about bend, things like beam and water. This one we'll see. But for now, what we'll work on in this module 1, you must know, is this one that will appear in module 1, these 3. Focus most of these 3. Tensile, compressive, and shear. So yeah, guys, bear with me there. Yeah, so that is it. So as you can see here, says the shape, size and the shape of a cross section. The size and the shape of the cross section influence the amount of force that can support or withstand. Fine. It is the meaningless to describe the strength of material without including information about its size. As you can see, the size also matters then. A thick steel cable is stronger than a thin cable. Obviously, we know. Let's say you have a rod which is thicker, and then you have a thin rod. Which one can you break it more easily? Is made up of, assuming this is made up of the same type of material, this obviously will be broken first, but this one will take longer because it's larger. That is the size of the cross section. Actually, what influences it's a cross section, the size there. As you can see, when we're talking about cross section, guys, we're talking about this is big, this is smaller cross section. So yeah, then as you can see, a relationship must exist between the size of the component and their force it may be able to resist, which is fine. Then there we have again for tension and compressive, the size of the corrosional area, it's important. The bigger the area, the lesser the deformation takes place. This is not true for long members in compressive as well. We'll discuss in module 10 about this. As you can see, it's fine. It was just an intro, nothing more. They won't ask you about those things. But as you can see, what is this? Remember, I've told you about this type of force. This is a tensile. This is like we are pulling. This is a tensile force, this type. But you see, this is a we are focusing on this as a small cross-section area, and then is thin. This is a big cross-sectional area, a small extended. You see the extension. If you are pulling, if I pull this side and I pull, you see there will be a large extension. That means this object will extend. That we call it the change in x. The change in length of that will this object will be extended. Wherefore, you see, it's when after the stretch will be like this force will influence it to stretch till there. But as you can see, the big one, the one with the big cross section, is only extends a little bit. As you can see, this size of x is small compared to the one. Yeah, so yeah, you see there an example. This is what we have, guys. This is a tensile force. Fine. These two types, and then remember, this is a direct. It's applied direct on the section. You must understand these are direct. This is a direct. Again, let me come here and tell you this. It's a direct one. These are direct. Applied exactly on the cross section. They are applied exactly on. These are not indirect. They are not applied on the cross section. The cross section, it is here. As you can see, the cross section of this, it's where there. This is a cross section. So these are direct force applied on the as you can see, show types of forces entailed. This is, you can see, this is tensile, we are pulling. This is compressive. As you can see, these two are direct. Two types of direct. We have two types of direct stress. Tensile and compressive are direct. You apply exactly on the cross section. As you can see, exactly on the cross section, it's where we apply our force. The force is applied exactly on the cross section. those, you call these things direct stresses, right? So hopefully guys you understand this. These are direct. The tensile stress is the result of pulling and stretching force makes a component long. As you can see, I've just told you about this. Compressive, we said this, rigid crushing or squeezing force makes the component shorter, as you have seen, right? To make the change clear, figure 1.7 shows these changes in length that they really are. The tensile stress make the bar longer while the compressive make it small. Obviously, when you compress something, we make it small. It's fine. As you can see, we apply, this is a tensile. Or you see the extension is represented by dot. You see the extension here. From there until there, this is the extension. Then this is the original length. Then you see those areas. But when you apply compressive, remember the original length was here, but it's constructed. Original length, as you can see, is there, but you have applied the compressive force, so this is reduced to this smaller size. Imagine from this big size to the smaller size, and then you see the construction they reduced there. Then we have our new length there. So this one new length is become longer, but this one new length is become short. We started by original length was long, this became shorter. The new length, original length was shorter but became long. So yeah, it's like this. You stretches when you're applying a tensile, you stretches. When you apply compressive, you shorten the object. You shorten the object. So tensile, as you can see, tensile stress stretches, while compressive you shortens the object. You shortens the object. Let's say we are tall, then we apply that. Yeah, you become short. I don't know, I'm playing there. Well, for this part of the syllabus, we'll use the same formula, both tensile. As you can see, we'll use the same formula for both tensile and compressive. Take note there. We'll use, for example, we have 1.3 there. 1.3 is clearly says we have given there a bar made of steel support a load of that. If the bar has a diameter of this, calculate the tensile stress in the in megapascal. So it's, you see that it's a bar. Is clearly if it is a bar. Example is I can do it like this. It's up to you which shape you want to place it, horizontal or vertical. It's one and the same thing. But take note, they say this tensile, and I said it's a pulling. That means there will be a force sound like that, a pulling, which is will be equal, this force will be 20 kilonewton. Actually, whereby this we can say it's a tensile, it's the same as tensile. Tensile is the same as the force. It's one and the same thing because measured in Newton. Also will experience another 20 Newton. Remember, this is a tensile, 20 kilonewton, not T. So kilonewton. As you can see, this is tensile and this is tensile. So yeah, those are tensile. And then remember, as you're applying this will change. This will be original length, but as you apply this will be long and there, and it will form some here. But we are not focusing on the change now. That is what I'm trying to explain there. Suppose those load, if the bar diameter, we've given this diameter right there of this cross section, the diameter they say is 15 millimeter. When you divide this by 1000, will be 0.015 meter. So do you agree with me there? Yeah. So says calculate the tensile stress in megapascal. So I want you to note um stress is, I want you to note something. Stress is equal to force over area. Also pressure is equal to force over area. Hopefully you know this. And then remember, uh what force is measured with. Its SI unit is Newton. But what about the area? The area is measured in meter squared or square meter. I want you to check. That means Newton per meter squared simply is equivalent exactly to what? Pascal. To Pascal. Are we good with that? So same applied. We said the stress, that symbol is for stress. We say it's force over area, whereby we said force is measured in newtons, but area in meters per squared. So it's simply that the stress is simply measured in what? In Pascal too. But this is, not make a mistake, this is a pressure, this is a strength. What I'm trying to say, you understand that. So must be very careful. You must be very, 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 very careful there. Hopefully you understand. But then they want us to calculate what? Calculate the tensile stress in megapascal. Meg. What is meg? Mega is times 10 to the power of 6. Okay, let's try and, okay, we will answer this question. Okay, let me answer this question first, then we'll try to do some convention a little bit. I want you to check some conventions that will be important to know your convention. Okay, let us do this. We've given the force there, which is 20, and we've given the bar diameter. So we know this force over area. We know that, can simply say, you know that an area is equal to pi over 4d squared. Remember, we are given diameter. Focusing, that means it has a cross section of what? Or focusing on the cross section is a cross section of what? This is simply what? A circle. So cross section of the circle is given by this, or other can say pi r squared. Depend on you. Still the area for a circle. So this is pi over 4. The diameter, I've said it was 0,015, right? Then do not forget to square. As you multiply your calculator nicely, supposed to get that this is 176,715 times 10 to the minus 6. Obvious is measured in meter squared or square meter. It's one and the same thing. We have now this. What about the force? The force you've been given. So this is easily like that. We can calculate the tensile stress, which is tensile. This will be simply what? Tensile stress. What is the force? We've given 20 kilonewton. This simply was 20 times 10 to the power of 3. Remember, kilonewton is the same like that. Divide by your area, which is 176,715 times 10 to the power of negative 6. Right, then if I'm punching this, I got, remember this is a stress. Our stress there simply equals to 113,177. This will be in mega Pascal. Hopefully you understand what is megapascal. Mega simply times 10 to the power of 6, right? That is times 10 to the power of 6. Let's say you're given a number like this, 1,000,000. then you want to go to megapascal, you divide this by 10 to the power of 6. You go to megapascal, you divide it if you want to write this in megapascal. So let's catch up some conversions. Converting, let us do some review. Let's say given millimeter squared, how can you convert this to become to be in meter? What is that? This is the same as mathematically. You take this as one thing, then this will be same as millimeter. But remember, from law of exponents, a multiplied by a will be a squared. So similarly, this we say we take it as one thing. They are not separate. When you're dealing with this distance, it will be one thing. So if this is a one thing, then will be, remember now we take one, but now they say they are two. This is same as multiply millimeter like this. When you multiply these two, will bring us back there. However, we can convert this in many ways. Let's say now single m, only m, meter is what is 10 to the minus 3. Also this is what is times 10 to the minus of 3. It's up to you that we want this to be what in meter, not meter squared. We want this to be in meter, right? Or we want this, or you can convert to be in meter squared. If you leave this these two, remember you've converted these twos, goes with that. Then that means this mathematically, when you add the exponents there, this will be times 10 to the minus 6. Then when you multiply these two, is same as meter squared. You understand? So if you want it to be in meter, multiply by also this by 10 to the power of 3 also. This will simply equals to what? 10 to the minus of to the power of 9 meter. So that it is from then till to there. You must know your conversions. You must know your conversion. Okay, let us convert this one. And let me just try and see if we can say number one. If I can say, let us convert 60 kilonewton to gigapascal. I want this to be, let's convert it to gigapascal. I want us to go there. So you must know your maths. I said you know that if Newton per meter squared is simply what Pascal, we will be only that Pascal. Now what about giga? Giga we know is 10 to the power of 9. So okay, let's check. Here we have 6. We can change this kilo. Kilo is the same as times 10 to the power of what? Of 3. We still have Newton on top, whereby we're supposed to get that Newton, which is fine. Then here on the numerator, we have two things, millimeter squared. I've said to you, this is the same as millimeter times millimeter. However, if we these two, remember 1 millimeter, 1 meter is equal to times 10 to the power of 3. Also another meter will be times 10 to the minus of 3. But when we multiply these two, will give us what? Meter squared. So this will simply equals times 10 to the power of 6 meter squared. So if this will be simple of times 10 to the power of 6, then we have meter squared. But what about this SI units? It is Pascal. These two is simply what? Pascal. So there we still have that 60 times 10 to the power of 3 over times 10 to the minus 6 Pascal. Remember, this is simply Pascal, but they say I want us to go to gigapascal. So we are still here. Mathematically, the bases are the same. You apply the laws of exponent there. As you can see, remember, if you have b to the power of 3 over b to the power of 1, this will be b power of 3 minus 1 minus this exponent to subtract there at the top. If you know your mathematics, then this is same as 60 times 10 to the power of 3. Then you minus, but it already have a minus, will be minus 6. Remember, you still have Pascal. Then this will be 60. If you add, multiply, that will be times 10, 3 plus 6. Still have Pascal. Then this is 60 times 10 to the power of 9 Pascal. But this, what is this? Times 10 to the power of 9 simply equals to gig. We have 60 like this times 10. Remember, this is simply what? Gig. Then here we have what? Pascal. So ladies and gentlemen, this is like this. So if you have mastered this, you won't take these steps. You'll go straight forward if you know your math. You know your conversion is important. It's main of conversion that you're supposed to know. You must do your preview on things like centimeter. See, on things like C, what does C represent? Things like C, which is times 10 to the minus 2 meter. You know, this is centimeter. C is cent. It's a cent. This times 10 to the minus 3. Things like these, guys. You remember, this M is not different. This small letter, but this big letter times 10 to the power of 6. Yeah, micro, if you still remember that. All this stuff, nanometer times 10 to the power of 9. Yeah, you'll see them. Base, this thing, know them, remind them. If you've given centimeter, you want to go to meter, you convert this, you'll divide by, remember that is same as what? Is times 10 to the minus of 3, right? So you want to go there. So 10 power of 2. So if you want to go there, remember law of exponents, this will be same as, if I take that to the down, will be same as m into 10 squared. Then this will simply divide by 1000 if you want to go to meet. We divide by 10, so by 100, not 10, divide by 100. So guys, this is what it is. So, and then also take a note, when you are applying, we're focusing, they say this is a tensile, we have a bar like this, we are focusing on the cross section. They say apply the force like this there. Also, remember there will be cross section. I want you to check, we're focusing on this cross section. They say apply, this is a tensile force. Making an example, this is a tensile force. We're focusing on this cross section of that bar. Now, mind you, sometimes you might be given a bar with a hole. They might trick you, but which is simple. They might give you a bar like this. They can project a hole there. So it depends. And then remember the hole goes like that until down if you have a hole. But if you did drawing, if you check, you view the front view. Example, if you view this side, if I view this side, the cross section, remember focusing on cross section, you'll have something like this. If you did drawing, there will be hidden details representing what the hole we've affected what Remember, this is a width. Here we have thickness. We have affected what? The width. The width. This hole will affect the width. Will affect the width. You understand? Will affect the width. So your area there will be equal to, the thickness is constant, is not affected. As you can check, will be thickness multiplied by what? Remember, it's of the rectangle is width multiplied by height, but we'll call it thickness, right? By now width, there will be width, we'll have width minus this hole, that hole there, minus that hole, the length of that hole. Depend will be how much that diameter of that hole, the length, which is, yeah, that diameter of that hole there. Subtract that hole there, the length, which is diameter of that hole, then you'll get that. So yeah, so far guys, this is what it is. So thank you for watching guys. This is what it is. So guys, thank you for watching, and please subscribe there if you have not subscribed, and share this to your fellow classmates, and then you can like and comment guys. Thank you for watching.